Hi everyone, welcome back to another video. So we're going through the Stroud Engineering Mathematics book and we're on chapter 9, the first part of it, trigonometry, and we're just on exercise 24 and 25 today, going through special triangles. Cool, let's get started. So we're going to read through the chapter or part of the chapter, and then we're going to answer some of the questions as well. So let's start with special triangles. Two right-angled triangles are of special interest. So two right-angled triangles, right, are of special interest because the trigonometric ratios of their angles can be given in surd or fractional form. That's fine. So if you don't know what surd and fractional form is, fractional form you're obviously used to. It's like 1 over pi or stuff like that. Surd is these. You should get used to it. Okay. So the first is the right-angled isosceles triangle. Okay. The right-angled isosceles triangle. An isosceles triangle is any triangle with two sides of equal length. Right. So if you had one line, and let's duplicate that line. Okay. And then you drew a line connecting these two together. Right, that would be an isosceles triangle because although it doesn't actually look at this side and this side are equal, right? And then this is obviously a right angle. Cool. So an isosceles triangle is any triangle with two sides of equal length. Okay. Since the angles of any triangle add up to 180, the angles in a right-angled isosceles triangle are 90, 45, and 45. Fairly obvious, but the 90-degree one's obviously here, and you got the 45 degrees, 45 degrees here. 90, 45, 45. Or in radians terms, pi over 2, pi over 4, and pi over 4. Pi is 180, right? So that makes this 90 degrees one here, pi divided by 2. And then half of 90 is 45, so pi divided by 4. Pi divided by 4. So basically, these here are in radians, right? And then obviously 45, 90, and 45 is in degrees. Alright, so or in radians, yeah, with side lengths. Therefore, in the ratio 1, 1, and then square root of 2, right? So remember in Pythagoras Theorem, a squared plus b squared is equal to c squared. Cool, so we can prove this 1, 1 to the ratio. So the ratio of 1 to 1 is the square root of 2. So we're saying that this is 1, this is 2, and this is square root of 2. So any other triangle that you have is either going to be a scaled down or scaled up version of these, right? So obviously remember in Pythagoras Theorem, 1 squared plus 1 squared is equal to the square root of 2 squared. Okay, so 1 squared is 1 plus 1 squared again, which is 1. So 1 times 1 is equal to 1, right? Is equal to the square root of 2 squared. The square root of something squared is just itself, right? 2, right? And 1 plus 1 is equal to 2. So here, this whole thing matches, or should we say this? It matches Pythagoras Theorem fine. So another way to look at it is if you use x. Whatever this length is here, this length, let's say it's x, this one's also going to be x, right? Because these are the same size, right? They're the same length. So this hypotenuse, the hypotenuse is always going to be whatever x is times the square root of 2. We just kind of proved that here by saying that, well, when these two are 1, then this is the square root of 2. But what this actually says here, the square root of 2, what we're not seeing is it's 1 times the square root of 2. It's this length or this length times the square root of 2. But because we're saying these are 1, we just omit the 1 here. But in the instance of calling them x, then you keep the x there. You can always remember that this triangle here is always going to be, its ratios are always going to be 1 to 1 in these two lengths, 1 to 1. And then this ratio here is going to be whatever this is, whatever these ones are, whatever value that is, times the square root of 2. And you can try it and it'll always be right. So here we see that sine 45 and cos 45 is equal to 1 over the square root of 2. And tan 45 is equal to 1. Okay, so let's explain that. We're saying sine 45 is equal to cos 45. Okay, so what do these words mean? Sine 45 opposite over hypotenuse, right? So, right? So opposite over hypotenuse, which is what? So what's the opposite here and what's the adjacent? So the opposite to this 45 is 1, and the adjacent is, the hypotenuse is square root of 2, right? So if you're going off of this angle here, we'll do it in different colors. Going off this angle here, then you've got 1 over the square root of 2. If you're doing it off of this angle here, we'll do it in green. Then the opposite to that is what? 1, and the hypotenuse is obviously the same, square root of 2. Obviously, it doesn't matter which angle you're using, whether it's the blue 45 or the green 45, it's the same thing, right? That's fairly obvious. Okay, So now we've established that sine 45 is equal to 1 over the square root of 2, which is what they've put here. So what about cos 45? Well, what's cos? We've done it already, right? Adjacent over hypotenuse. So you should see where this is going, right? If you don't, just please take a look over at this triangle. Think about it. Adjacent. So think about it. Adjacent over hypotenuse. So what's the adjacent of either one of these 45? So whether we're looking at this angle here or we're looking at this angle here, what's the adjacent? The adjacent to this one is 1, and adjacent to this one is 1. So you've got 1 over, and then the hypotenuse again remains the same, square root of 2. So we have the exact same answers here. So sine 45 is equal to cos 45. Now that's not the case for all triangles, but it is the case for this special right angle triangle, because why? These two are both the exact same value, meaning that they have the exact same ratio. So whether this is 1, 10, it doesn't matter. Okay, so then let's look at the last bit. It's got tan 45 is equal to 1. So what's tan? Let's work it out. Tan, as you can see here, is opposite over adjacent, TOA, right? Tan 45 is equal to opposite over adjacent. So now hopefully from here you can see how that equals 1. Opposite is 1, obviously, and adjacent is 1. Can't see that? Pick any angle. TOA 40, tan 45 here or tan 45 here. Doesn't matter. Tan is the opposite, or in this instance the opposite, over the adjacent or over the adjacent. Both of them are 1, right? 1. So it's 1 over 1. 1 over 1 equals the grand number of 1. That's what we've got here. If that was too fast for you, don't worry about it. Just go over it again. You work through it yourself. Just keep in mind sohka toa, and you'll be more than fine. Cool. Okay. And then so, or measuring the angles in radians. So it's just doing this exact same thing again, but in radians. So the important thing is here we're dealing with radians. This is radians here. All of this is radians. If we think about radians, pi radians, right, is equal to 180 degrees, right? That means that 90 degrees is equal to pi divided by 2, and 45 degrees is equal to pi divided by 4. Divided by 2, that's supposed to say. Pi divided by 4. Okay, so we've already explained this, but this is basically what we've already covered over here. We covered it all here, but this is in its degree form. This is in degrees, right? And then this what we're covering here is in its radian form. So there's no need to reprove everything, but I'll just cover it just so you fully understand it. So sine 45 is equal to cos 45, right? We know that. So what's sine 45 in radians? Well, that's the same as sine pi over 4. Correct? Likewise, the same with cos. Yeah? And we've already showed over here as well that the adjacent over the hypotenuse equals 1 over the square root of 2. Or the opposite over the hypotenuse is equal to 1 over the square root of 2. Because this 1 here represents the sides of equal lengths. Whether it's the opposite or the adjacent doesn't make a difference. It's always going to be 1. So one thing we can say is that sine pi over 4 and cos pi over 4 is equal to 1 over the square root of 2. We likewise prove tan 45 is equal to 1. And so then tan, what's 45 in radians? Pi over 4 is equal to what? 1 again. Correct? And if you've forgotten, we prove this here. Tan 45 is equal to the opposite over the adjacent. What's the opposite? What's the adjacent in terms of ratios? 1 to 1, right? So 1 over 1. 1 over 1 equals 1. Cool. Move on. Hopefully that's clear. So now let's use a problem. A prop in the form of an isosceles triangle constructed out of timber is placed against a vertical wall. This being a vertical wall. If the length of the side along the horizontal ground is 3.4 meters, the length of the hypotenuse to 2 decimal places is found as follows. So remember that this is x, right? This is also x. So x is equal to 3.4 meters. We know that because these two are the same length. And then we know that this is the hypotenuse. And to get the hypotenuse, it's the square root of 2 times x. literally for us to work out the hypotenuse is equal to 3.4 times square root of 2. So let's work that out. 3.4 times the square root of 2. Let's work that out. 3.4 times the square root of 2. That gives us 4.808 or 4.81, right, in terms of meters. And that's what we've got here, 4.81. Cool. So now one for you to try. A bicycle frame is in the form of an isosceles triangle with a horizontal crossbar. So horizontal crossbar forming the hypotenuse, right, and that's 53 centimeters long. The length of each of the other two sides to the nearest millimeter is. So you want us to find x. Okay. So if we look at cos, we can use cos or sine here. Why? And we can't use TOA because, sorry, I should say tan. Right? We can't use tan. So cos, sorry, sine is so, cos is ka, and tan is TOA. So both sine and cosine have a hypotenuse, which is what we've got here. Tan, TOA obviously doesn't have any h for hypotenuse. Okay, so whether you use sine or cosine 45, it doesn't make a difference. It's obviously 45 because this angle and this angle is 45. So this sine or cosine 45 is going to be equal to the side, right? Whether it's the adjacent or the opposite, it doesn't make a difference. The side over the hypotenuse, right? And we know that, so we've got sine or cosine 45 is equal to the side, which is unknown. Right, we can call it x for now, over 53 centimeters, since it's obviously a hypotenuse is 53 centimeters. Now we can simplify this even further because we know that sine 45 and cosine 45 is equal to 1 over the square root of 2. So we can say that then that is equal to x over 53 centimeters. To find out x, we simply do 1 over the square root of 2 times 53 centimeters, and I'm going to guess that gives us 37.5 centimeters. And if you see they've taken the side length divided by the hypotenuse, we know the hypotenuse is 53. We know that because we've got the side length, it's either this side length is either going to be opposite or it's going to be adjacent, one or the others, right? And then so we know that since we've got O and A and the hypotenuse, it's either going to be so or ka. So they've chosen cos 45 and then they've transferred cos 45 into 1 over the square root of 2, and then they've actually worked out the decimal form version of that, and then they've multiplied that by 53. This is a slight longer way of doing it, but I assume they're just going through all the steps for beginners. Cool. Alright guys, so that's it for me. I'll upload these notes to my Dropbox. You find the link in the description. And yeah, if you enjoyed it, leave a like. If you have any questions, drop a comment below. If you have any suggestions, likewise drop a comment below. And I'll see you guys in the next one. Peace.